This week we round out our discussion of natural deduction by going over the 9 rules of replacement. These rules are a little bit different than rules of implication. You see, with rules of implication, those particular rules apply to the forms, valid forms that are within arguments. Rules of a replacement, however, are basically demonstrating that certain kinds of propositions can be logically equivalent to one another. And as I discussed in the instructor note in the module, I've sort of laid out how logical equivalence works, but basically if you were to take 2 propositions that are equivalent, then you would see that on every line of the truth table under the main operator they would have the same exact truth value. It's basically what the rules of replacement pick up on. So the other thing, the thing that's relevant about rules of replacement is that sometimes we need to find the logical equivalent rather, to some sort of premise within the argument in order to derive the conclusion within natural deduction. Sometimes the actual conclusion itself is in a kind of form that you wouldn't readily see within the proof. And so that's basically the function of rules of replacement. Now, rules of replacement are also different from rules of implication insofar as with rules of implication, as I discussed last week, you have to apply the rule to the entire statement. With rules of replacement, you can apply the rule to parts of the statement. Okay, so now you get to kind of work on parts that you want to work on with these rules of replacement. Now again, as your book the selection from the book describes it, rules of replacement are so-called two-way streets, right? So that's why we use these colons here to symbolize that if you had this form, for instance, if you had on the first line here, the De Morgan's rule, if you had this within your proof and you somehow needed to get this here with the main negated conjunction, then you could go that way. You go this way or this way, depending on what you need within the proof. That's the idea with rules of replacement. They serve the needs that you have when you're trying to derive the conclusion within a proof. So let's go over each of these first 5 rules of replacement here. So the first one that your book discusses is the De Morgan's rule, and or DM. And the way that De Morgan's rule applies to conjunctions and disjunctions. The best way to keep in mind how to do De Morgan's rule is that if you apply De Morgan's to for instance, to a conjunction, or let's just say this, if you applied the De Morgan's rule to a conjunction or disjunction, you will do 2 things. So this is for DM. So 1, you will switch the main operator from the ampersand to the wedge, or from the wedge to the ampersand. And then you will take out tildes where they had previously been, and put in tildes where they had not been before. So for instance here, I'll just take a kind of like example. If you had something like, for instance, something like this, not K or P, according to De Morgan's rule, the equivalent to this particular disjunctive statement would be the following. So first of all, we're going to keep our letters in here. So we have our K and we have our P. But now we're going to switch the connective here to the operator here to an ampersand, and we're going to take out the tilde in front of the K, and we're going to put a tilde in front of the P, but there's always 3 spots in these compound statements. There's always 3 spots for tildes. So once we've taken the tilde out in front of the K and put it into the P in front of the P, then we have to put a tilde in front of the whole statement, because there were always, in any given statement, there were always 3 spaces for tildes. So you have to put them in where they had not been before and take them out where they had previously been. And that's basically the way that De Morgan's works. And it can work either way, essentially. So it's a fairly kind of straightforward rule here. Now, the next rule is kind of I consider Rule 2 here and Rule 4 here to be kind of like formalities in proofs. You might wonder why you might have to do them, but that's just part of the procedure for deriving the conclusion. It's like the proper steps we're supposed to take. Again, you know, what we're always doing in proofs is we're showing the work that's going on within the argument. I mean, the argument's already valid, but we're just kind of drawing out and showing step by step every little move that's made. So you might think rules like commutativity in 2 and double negation on 4 are kind of, you know, unnecessary rules, but they are part of the process of deriving the conclusion, so they are an essential part. So commutativity here just simply says that if you have a conjunction or a disjunction, you can switch the sides on which the disjuncts or the conjuncts are on. We kind of talked about this way back when we did translations. If, for instance, you had something like, looking right here on the original conjunction here, if you had Nancy and Barbara are going to the fair, that statement is logically equivalent to Barbara and Nancy are going to the fair. It doesn't change the truth values between the two of them. It doesn't matter which order you put these letters. Same goes for the disjunction. So you might wonder why you would ever need to use the rule of commutativity. It's kind of a hard one to say too. For instance, there's certain like real formalities that we didn't really go over in the rules of implication, but we can talk about them now that we have these rules of replacement. But for instance, technically, according to the rule of disjunctive syllogism, technically, for instance, you can, if you have this statement, you can only negate whatever's to the left of the wedge. Okay, so technically, by a certain kind of formalism, you couldn't do this just straightforwardly, just go P or Q, not Q, therefore P. According to the formalities of derivation here, you would need to first, if you really wanted to, so say this is your rule, this is one of your premises, and then you have the negation of Q, and you're trying to get P, all right, here, you would have to do the following. You would first have to switch the sides that the P and the Q are on, using the rule of commutativity. So here we go. You switch it around, and that's on line 1, using the rule of comm here, commutativity. And then you can go, for line 4, you can go on lines 2 and 3, using the rule of disjunctive syllogism. You can then therefore derive P. It's again a formality. Another rule where comm comes into play, or another kind of instant rule of implication where the rule of replacement of commutativity comes into play, is, for instance, if you have something like this. Say you have, oh, I don't know, a conjunction like K, let's just say K and P, and you're trying to derive P, okay? So you might think, and the kind of the way you were doing it last week for a while, is you might just go ahead and just derive that P from this conjunction using simplification. But according to the formal rules here, we can only derive the letter that is to the left of the ampersand. So now that we have the rule of comm here, we have to then therefore switch this around and go P and K using line 1 and the rule of comm here. And then, and only then, you can therefore derive P on line 2 using the rule of simplification. Again, it is sort of a weird kind of rule. You know, sometimes in certain logic books they will not actually show you the rules of commutativity or double negation. They just sort of cut to the chase. But given the system that we are using, we will use these rules. Okay. All right. So while we're on the subject of these sort of formal rules here, let's go ahead and talk about double negation real quick. So double negation is sort of self-explanatory, and it was kind of always there. Double negation just basically says that a single letter P is equivalent to tilde tilde P. Okay, double tildes here. And the way this would come into play would be sort of in the following way. So say you have a conditional like Q horseshoe not B. Okay, and then you have a premise B. Okay, and you're trying to derive not Q. Well, again, last week you would say this is just straightforwardly an instance of using modus tollens. And so, yes, technically that's what you are going to do in the end, but in order to adhere to the specifics of this system of logic, you will need to first make that B into a tilde tilde B. Because, again, the rule of modus tollens always, the formal way in which we write modus tollens here, like the way it's often demonstrated, is that there's a negation here of the consequent, which then therefore gets you the negation of the antecedent. So if you have this case where you're going to have to use modus tollens and the consequent is already negated, you will then need to use double negation. So here we go, we have not B, and that's using double negation on line 2. And now you can then therefore derive not Q from lines 1 and 3 using the rule of modus tollens. And so again, 2 and 4, rules 2 and 4 on this board here. They're kind of weird rules, but they're basically there for us they're basically rules that you just ought to follow, given the system that we are working with here. Okay, so I have to sort of accept this on faith, basically. All right, so the other remaining rules here that we have on the board. So the rule of associativity here, basically all that this rule states is that if you have an instance where you have 3 letters being either disjoined with the wedge, and all of the operators are wedges here in this case, or 3 variables being conjoined with 2 ampersands or so, what this basically says is that you can move the couplings here. You can move the parentheses and couple different parts of either the disjunction or the conjunction. And again, you might wonder why this is sort of necessary. Well, this one has some actual, I don't know, it's useful here because, for instance, let's just say that you had something like, I don't know if you had something like A or P or X, okay? And then you had not A or P, okay? And you're wanting to get X. Well, and if you had to sort of think backwards before with the rules of implication, you really have to kind of think backwards with the rules of replacement. You're trying to get the X out of the way, okay? And you can see that you have it up here on line 1. And you can say to yourself, okay, so if I was able to sort of get that X no longer associated with the P, then I could maybe use a disjunctive syllogism to derive it, okay? Because again, disjunctive syllogism and constructive dilemma, but in this case, disjunctive syllogism works with disjunctions here in terms of the rules of implication. Right. And basically, yeah, you can see here you have A or P at the negation of it, and then you could hypothetically have A or P right here. So this is a helpful rule because what we can then do here is on line, for our line 3, operating on line 1, we can just say, using the rule of associativity here, we can then therefore move the parentheses from the coupling the P and X to coupling the A and P, right? So 1 ASSOC, okay? And then now, well, we have here the opposite of the left side of the disjunct, and we know then that we can use on lines 2 and 3 disjunctive syllogism, and then therefore derive X. And that's how it's useful to use associativity here. Another way, if you have conjunct, consider that you have like a claim, like we'll just use the same letters here, so A and P and X. Well, hey, say for instance that your conclusion is A, right? And you say to yourself, well, I know with the rule of implication, specifically simplification, I could get A out. But see, I can't get A out as long as it's tied together with this P. And so what you can do here is, using the rule of associativity, you can then go A and P and X, and now basically join together P and X. Right, so this would be like associativity. And then you could then therefore simplify out A. Okay? Right, and get your A out. So again, associativity, a lot of these rules are very useful, right? When you're kind of, trying to get something, but you can't really figure out how to, get your conclusion out of certain premises. It's very helpful to use these rules because they can kind of get you to where you need to go quicker. Okay. All right. So let's discuss the very last one on the board here, which is distribution. So this one here operates on conjunctive and disjunctive statements. And the way that this works is that if you have, for instance, a statement where the main operator is an ampersand, like on the first line here, what it says is that you can then, therefore, the equivalent of this is basically the disjoining of the two conjuncts, where the conjuncts include the first letter here to the left of the conjunct, to the left of the ampersand on this side, and the disjuncts on the other side of it. So it might be kind of helpful to maybe give an example here. So I don't know, if you could say something like, Peter is going to the movies and Quincy or Rachel are going to the arcade. Okay. So another way of putting this statement is the following way. So the other way is to say that either Peter and Quincy, or excuse me, I should say, let me rework this here. Peter is going to the movies and Quincy is going to the arcade or Peter is going to the movies and Rachel is going to the arcade. The main point here is that Peter going to the movies is a necessary feature of this statement in order for it to be true. But it can either be Quincy going to the arcade or Rachel going to the arcade. The idea here is that these are equivalent statements here. Basically, it's a way of spelling out, if you will, this first statement. Likewise, it works the opposite way with when the main operator is a disjunct. So if instead you said Peter is going to the movies, or Quincy and Rachel are going to the arcade. In other words, you're saying Peter is going to the movies, or Quincy is going to the arcade, and Peter is going to the movies, or Rachel is going to the arcade. So again, these are just basically spelling out this first statement here.